I'm going to be talking about the impact of number representation for high-order implicit large-eddy simulations. As I guess you guys all know, as we've been talking about, LES is expensive, really expensive. It's orders of magnitude more expensive than doing a RAND simulation. And so we're interested in anything we can to reduce the cost. Now, typically, when we do arithmetic on a computer, we follow this IEEE 754 standard. And the two main things we consider are single precision floating point numbers, which are 32 bits, and double precision floating point numbers, which are 64 bits. And I've just got a diagram here which shows the rough structure. The idea is you have a sign bit, a mantissa, which is between 0 and 1, times 2 to some exponent, with the bits allocated as shown below. Now, one of the things to note about computer arithmetic is it's complicated. And it's one of those things where if you think you understand floating point arithmetic, you don't. It has a whole number of quirks with subnormal numbers, denormal numbers, rounding modes, correct rounding. It really is a rat's nest that can fill several interesting books. But nevertheless, it's worth investigating at some level, as when we look at accelerators and hardware that's coming on the market, one of the things we observe is there is an increasing disparity between our ability to do single precision computation and double precision computation, as I'm showing in this table here, which shows the capabilities for various hardware platforms. They're a couple of years old now, but the trend hasn't changed too much, where you can see that whereas traditionally single precision arithmetic was 2 times quicker than double precision arithmetic, we're now seeing hardware where that ratio is a factor of 16 or even 32 in some circumstances. And hence, if it's possible to use single precision arithmetic for our simulations, then it might be possible to greatly reduce the computational cost and or expense of these simulations. So what kind of speedups can we look to get then by taking our code and doing a wholesale port from double precision to single precision? Well, if a particular kernel is limited by flops, then according to that table, it's somewhere between 2x and 32x. If a kernel is limited by memory bandwidth, it's a factor of 2x on account of the fact that a single precision number is half the size of a double precision number. If it's disk I/O, writing stuff to disk, the case is exactly the same as with memory bandwidth. It's a factor of 2x. And if what's limiting us isn't bandwidth but latency, then we expect no change, as it's only throughput that improves, not latency. Now, for preparing this presentation, I did extensive research in a wide number of bars in the area, and I came to the conclusion that if given the choice between a single and a double, the double wins every time. And it would appear as if CFD codes are no exception to this rule, with the majority of CFD codes being double precision. And in fact, especially in the unsteady space, very little research has been done to if we actually need double precision arithmetic. Results in the steady state space, so this is say for RANDs, do show, I'd say reasonably conclusively, that you do need double precision arithmetic if you want to get a reasonably well converged solution. But there really is nothing in the literature for unsteady simulations, where we're looking at collecting time average statistics for simulations that are predominantly under-resolved. And so this is what I set out to investigate. My methodology was relatively simple, and it was to rerun several of our previously published test cases using exclusively single precision arithmetic, and then compare the results and assess the performance Okay, so what did we do? Well, we took our code, pi file, and several unsteady viscous test cases, because they're the ones that are most useful and most representative, specifically Taylor-Green vortices, which we've seen a lot of today, flows over a circular cylinder, which we've seen a little bit of today, and flow over a NACA 0021, which we haven't seen so much of today. So, 3D Taylor-Green Vortex, which is a very standard test case for DG and FR codes. You start off with an analytic initial condition inside a periodic box that consists of some large coherent structures, and then over time, those structures break down until viscosity does its thing and kills off the simulation. I ran a sequence of simulations on 4 structured grids with a roughly constant degree of freedom count, aiming for approximately 256 cubed overall degrees of freedom, with varying numbers of elements depending on the specific polynomial order, with this being roughly the resolution that's needed for DNS. In the table, I'm showing the amount of memory, so storage or RAM required for the single precision and the double precision cases across the board. And the first thing we note is that indeed switching to single precision does result in a meaningful reduction in the amount of memory that's needed, although it isn't exactly a factor of 2x, because you've got to keep some pointers and tables around to account for the grid and the such like. Okay, so let's take a look at the results. The first quantity we're going to look at is the kinetic energy decay rate, and we're going to compare with the spectral DNS data of Van Rees et al. So for the 4 plots I have on the right, we have normalized time along the x-axis, and along the y-axis we have the negative kinetic energy decay rate, and I've just normalized it by 10 to the minus 2 to clean things up. We have our 4 different simulations at 4 different polynomial orders, and the first thing we note is that we get very good agreement with the DNS data, with the agreement getting better as the polynomial order goes up. That's expected based off the arguments I made in my previous talk around resolving power per degree of freedom, but the critical point is there is no substantial difference between single and double precision, even for this canonical, slightly pathological test case that's known to be very twitchy in many regards. Okay, so how did the performance work out? Well, it's not on a particularly large case, but I ran it on a pair of NVIDIA K40Cs, which are a GPU. And what I want you to focus on is firstly this gigaflop per stage number, which is roughly constant. What this basically means, and it's just interesting to highlight, is that on this particular simulation, on this particular kind of grid, the amount of work we need to do per Runge-Kutta stage does not increase as a function of the polynomial order. So here it's not true that higher polynomial orders incur more work per degree of freedom. And this is a general property you'll find on hexahedral grids. But the key thing to draw your attention to is the speedup number, where we can see that the speedup is between 1.8 and 3 by switching to single precision. And although I'm running a bit short of time, I won't go into detail for the P5 results as to why we get a speedup factor of 3 rather than the factor of 2 we expect. But if there's time at the end, ask me and I can explain the origins of this. But so far, so good. No impact on accuracy, and we've got a decrease in memory usage and a real tangible performance in terms of runtime. Okay, so let's now go on to flow over a circular cylinder. This is the exact same cylinder that that Tariq was talking about in his talk with pans, except I'm running on a mixed prism tech grid. It's of span pi d. It's at Reynolds number 3900, effectively incompressible Mach number of 0.2, and p equals 4 solution polynomials. So a reasonably realistic simulation. Mixed grid, unsteady, reasonable Mach number. Let's take a look at the results. So the first thing we're going to look at here is the pressure coefficient on the surface. Now, this particular case is a little bit quirky in some regards, as the cylinder itself has two distinct shedding modes. And so this is why you see when I'm comparing with the LES results of Lemukel that we have two lines. One of those lines is for each of the modes. And so when you run this simulation and take a time average over a reasonably short period, you can get one mode, you can get the other mode, or you can get a blend of the two modes. And what we see here is that pi-FR with single and double precision is not statistically different. The results are different, but again, this is something that is expected when you run these unsteady cases, as when you kind of start them up, there is an initial transition to turbulence that's very sensitive to your initial conditions, to how your domain has been partitioned, etc., etc. And so differences on this level are not unusual. The differences between single and double are at the same level we would expect as if you ran pi-FR double precision on two different pieces of hardware or on two different grids. Performance for this particular case improves by a factor of around 1.6 by switching to single precision. So a bit less than what we saw with the Taylor-Green Vortex. And this is a consequence that when running on tetrahedral grids, you have a fair bit more indirection going on than on a structured hexahedral grid. And as I mentioned a few slides ago, when we have indirection, or that is a substantial factor, we don't expect to see any substantial improvement. But nevertheless, a factor of 1.6 is still a factor of 1.6 for no substantial impact or systematic impact in the results. The final case, this is by far the most challenging, is a NACA 0021 at 60-degree angle of attack. This was originally run by Jin Sok. It's at a Reynolds number of 270,000, Mach number 0.1, and we're going to compare with a set of experimental results. So the grid here had 206,000 hexahedral elements, but in an unstructured extruded grid. The span is 4 times the chord, and we're going to run with 4th order solution polynomials and a full, as in surface and flux anti-aliasing, as this is very much an under-resolved case. And the key metric that I want to focus on here is the power spectrum density of the lift coefficient, as this has proved to have been very difficult to get right with both LES and other solutions. And what we can see here is, again, compared to the experiment, the single and double precision results for pi-FR capture both of the peaks, which are the key things that we want to try and pick up on, with otherwise no systematic differences between single and double, and they're both picking up on these peaks, which is effectively what we're looking for in this case, and what's previously proved challenging for other codes running at a lower level of resolution. So this is an extremely challenging test case that took a very long time to get right, as it were, but here when we took the exact same setup, right, single precision, no issues. Okay, so what's the performance difference here? Well, since we're looking at an anti-alias case, the operator matrices here, just due to the way things were set up, are all dense. I really pushed us out near the limit of strong scaling because this is a very expensive test case. You have to run for hundreds of passes over the chord. And so it takes a very long time, hence I used a lot of GPUs. And what I observed was an overall speed up of 1.8, which again is very respectable considering it cost us almost nothing in terms of the accuracy of the overall results. So to not pontificate too much, I'm going to make the somewhat bold statement that someone is welcome to disprove if they have the data, but I'm going to claim that for LES, single precision does appear, based off the data I have, to be sufficient. And so if you're running such a simulation, I would suggest it's worth trying it in single precision, running it along with double precision, and if you don't see any substantial differences, continue with the single precision simulation, stop the double precision simulation, as as it's going to be substantially cheaper